let's get going. My name is Jim Dowling. I'm CEO and co-founder of Hopsworks. I'm joined today by my colleague Javier de la Rua Martinez, who's a research engineer at Hopsworks. And we're going to talk today about DeepSeek R1, sovereign AI with DeepSeek R1, and how we do that in Hopsworks. A little bit of a joke here. I mean, everyone's talking about DeepSeek at the moment. Accusations of it using data taken from OpenAI. OpenAI itself is in a court case with New York Times over data it's taken from others. So there's a lot of things happening in the space, and I'll try and give you a deep dive technically on what DeepSeek R1 is, what its innovations are. That'll be the first part of today's talk. I'll talk a bit about sovereign AI and how DeepSeek R1 levels the playing field. So that means that now if you're in an air-gapped environment, maybe in some data center that's not a public cloud, you're not going to be disadvantaged because you won't have the best model. And then we'll conclude. Javier will do a demo. Hopsworks, who's going to run DeepSeek R1, the quantized version of V3. He'll also show you how we can host a distilled version as a deployment on Hopsworks with K-Serve and VLM. And a lot of the work that I'm taking today will be based on the technical report that DeepSeek released on their version 3 of the model, of the R1 model. It's a good paper, and I'd recommend you reading it. I'm going to start with the DeepSeek deep dive, let's call it, on DeepSeek. And in particular, what I'm going to do is look at some of the innovations in DeepSeek. But before I do, I'll just tell you a little bit why we're talking here. We work for Hopsworks. So Hopsworks itself is a data platform, a software data platform for managing data for AI, but it also provides compute. So you can deploy, fine-tune, train models on Hopsworks, and it's built on top of both lakehouse data and real-time data. So as a platform, if you want to try it out, there's a free version available called HopsworksAI.ai. Over 10,000 people using it. We are used as a company in production at Fortune 100 companies, billion-dollar companies in the public sector. And a lot of what we're talking about today in terms of sovereign AI, Hopsworks is running in air-gapped environments today. So without further ado, let's jump into what DeepSeek is. So DeepSeek is part of a new family of large language models that are based on what are called chain of thought reasoning. Now, I'm a very heavy user of large language models. I like Claude, I like GPT-4.0, and I use them in my day-to-day work to do things like programming or to get feedback and ideas. And the chain of thought reasoning models are slightly different. What they do is they'll explain why they've answered a question in a certain manner. Now, this is a question I wrote in yesterday. Tell me a random funny fact about the Roman Empire. And it took quite a while to answer, and this is on a hosted endpoint. And it gives you some ideas of its thinking. The answer in the end is Emperor Caligula planned to elevate his horse to the high office of consul. So it was a high political office in the Roman Empire. And the way it got to that answer was it started thinking about what's funny or what was unusual in the Roman Empire. And lots of things like using urine for mouthwash and the vomitorium. These are considered funny in a kind of a jokey, maybe, toilet humor manner. And it came up with that joke. But for any question you ask it, they'll go through the reasoning that the model had for coming up with its answers. So, if you're a comedian and want to come up with a joke, it'll tell you how it came up with the joke, which is not something you traditionally find in comedy. So that's what DeepSeek R1 is. It's a new family of model called chain of thought reasoning, and it performs amazingly well. The innovators in this space have primarily been OpenAI with their O1, and now currently their O3. The O3 mini model is available, and DeepSeek is on a par with those. So, the performance we can see for MML use slightly less. I'll talk a little bit about that later on, but in general, it's on a par with these very expensive models. Now, why a lot of people are really interested in DeepSeek 1, and why we see a lot of happenings in the global stock markets, is because there's an assumption that it changes the economics of AI. And the economics of AI, it's kind of, if you go back to 2008, remember we had a huge the great financial crash. And the great financial crash was in part caused by something called the Black-Scholes equation. It's an equation for setting the price of assets. Very interesting movies you'll see on that topic. But there was an overuse of that equation, and then too much money was placed in risky assets, particularly related to home mortgages, and the whole system went down. AI has built on something called the let's call it the large language scaling law. Right? The large language scaling law is well known in deep learning that if you have a doubling in the amount of compute, your data set, training data set size, and then the size of your model, you'll get roughly a logarithmic improvement in the model performance. So this diagram that you can see here shows you that the logarithmic relationship between compute, the amount of compute you use, and then the test loss, the amount of data that you use to train your model and the test loss, and then the number of parameters in your model and the test loss. And there's been some small, changes. You'll see, for example, Llama 3 models use a bit more compute, and that worked quite well. The former chief scientist of OpenAI, Ilya Sutskever, at NeurIPS in December came out and said, well, there's going to be minimal marginal gains from that. So the training phase of large language models massively improving in performance is starting to tail off. So what the implications for that we'll see in a second is that we're moving from adding a lot more compute at training time, this pre-training time, to inference time. Now, the reason why the markets were also interested was because of the cost. So the total cost in just training was estimated at $5.5 million compared to tens of millions for their competitors, but it really doesn't break this scaling law. What we'll see is that there's been a number of small improvements that have reduced the cost and of training, but nothing that actually breaks these scaling laws. So the first point I made there was that there's now a talk that because of pre-training is not going to keep improving, it's not going to keep growing to the sky. Trees don't grow to the sky. So where we're going to see the next set of improvements in AI and large language models, and most people are saying it's through scaling up compute at inference, or what some people call test time. So I prefer the term inference time. Inference means when you're making predictions. And the three main phases in training any AI system are your feature engineering, so getting all the data that we're going to use to train our large language model with, cleaning it. That's feature engineering phase. Then we have the actual pre-training of our large language model and additional post-training phases like supervised fine-tuning or preference alignment. And that's where all of the compute is being used. So the tens of millions of dollars used to train many of these large language models has gone into the training phase. That's beginning to level off. And now we're seeing that if we invest more money in inference time, so we do more compute at inference time, we can also improve predictions made by our large language models. And that's where these chain of thought models, including DeepSeek or1, as well as OpenAI's O1 and O3 models, what they're doing is they're making repeated calls to large language models with the goal of searching for better answers within the kind of some sort of planning space. So those repeated calls all cost in terms of compute. You're gonna make a call and say, should I do this? And then you get an answer. Well, I think this is my answer. I'll take the next part. And so all of the calls in the chain of thought require additional calls on GPU infrastructure or any accelerator, hardware accelerator infrastructure. And that's what, when people say we're doing more compute at inference time, that's what they're referring to. So we can say is we're shifting right compute from training to inference time to try and make sure that our AIs keep improving in prediction performance. So let's dive into some of the innovations in DeepSeek R1 v3. And this is, I'm going to go relatively quickly through this. The main one people talk about at a high level is that all prior large language models, the well-known ones, have gone through three phases. They pre-train on massive amounts of clean text data. Then they'll do supervised fine-tuning on a instruction data set, so with questions and answers. And then they'll finally do preference alignment with something like reinforcement learning human factor based on some questions, and then the preferred responses to those questions and non-preferred responses as well. And that's been pretty standard. So what DeepSeek saw was that, well, let's kind of skip this supervised fine-tuning phase. They don't entirely skip it because they're actually doing a bootstrap of the reinforcement learning phase with some supervised fine-tuning. But in general, they're saying, okay, if we just use reinforcement learning, to optimize the pre-trained model for this chain of thought reasoning, it works really well. And what they do is, in particular, they have something called rule-based reward model for reinforcement learning, where you can train the model with things like, here's a program, and then you try and make sure the program compiles. And if it compiles, then you'll say, great, that's a preferred response. If it doesn't compile, that's not preferred response. If the program that you write gives a particular output, that's a preferred response. And if it doesn't give you that output, it's non-preferred response. So you can generate a lot of the training data sets for this reinforcement learning phase through what's called rule-based reward model. So it's not going to be using a neural network to estimate the reward model. It's going to be using accuracy rewards and format rewards. There is something called group relative policy optimization algorithm that's used. And then there is also this cold start fine-tuning phase that they've added to initialize the reinforcement learning actor. So that's the first innovation. The second innovation is something called the mixture of experts model. So in mixture of experts model, we can see in the bottom left-hand corner here, we have this traditional mixture of experts model. So we have an input comes in. Now, in this case, the input isn't routed to all of the blue boxes. We've got n blue boxes. It's only routed to 2 of them. So we set k to be 2. So that means that the forward pass in this model is not going to go to all n experts here. Each box is considered an expert. You'll only go through 2 of them. And this will reduce the total amount of compute required to produce an output. So in DeepSeek or 1v3, there are 631 billion parameters in total, but only 37 billion are activated on each forward pass. So what's different in their version of mixture of experts is that they don't just have it, they have k equals 3, so they're going to pick 3 experts, but they also have a shared expert that all of the forward passes will go through as well. So it's a slight innovation, nothing extraordinary here, but what is quite extraordinary is if you look at the performance of this model, the 16 billion DeepSeek MOE model, if you can see for 16 billion parameters, it's an outlier compared to the existing LLMs. So that means for a lower number of activated parameters, it's getting much higher performance than its competitors. So this is an innovation that's contributing significantly to the improved performance. Another innovation is something which is extending the traditional transformer model called multi-head latent attention. And attention we've known from the original Transformers paper, this idea that, you know, if I have a word coming in here, let's say the word bank, in English, the word bank can mean many things, from a place there's money deposited to the side of a river to the bank of a hill. Each of these attention heads, or each of these heads here, are able to capture different contexts for that word that could mean different things in different syntax relationships or semantic relationships. And by having multiple heads, we can capture all of those meanings and agglomerate them together in a single output. But the price we pay for it is a lot of redundant computations. We've copies of these keys and values in inference. We've got 8 heads here, so we've got 8 copies of them. And this costs a lot in terms of memory, and it costs a lot in terms of compute. So there's been a lot of optimizations for multi-head attention to basically say, okay, well, what if we just share the values and keys over all of the queries? That's called multi-query attention. It didn't work particularly well. It wasn't, in terms of prediction performance, it wasn't super stable. And then grouped query attention did work much better. Minor performance hit, but much reduced inference latency. What they've done in DeepSeek v3 is something different. They keep all of the attention heads, but now they're compressing them. So they're compressing them into a latent representation, and that reduces the amount of memory required for them. And that seems to work very well. So we can see here that the key value cache per token, the size of it goes from 860 kilobytes down to 34 kilobytes, and this improves latency. It's building on so how's it compressing them? Well, it's compressing them with something called low-rank approximation. You may have heard of that idea from LoRa, which is used to fine-tune large language models with a smaller adapter model. So you keep your model parameters fixed, but you have the smaller adapter model. This is different because this is trying to reduce the bottleneck for the KV cache in the forward pass for inference. But it's using the same general idea that there are low rank approximations of, in this case, the keys and values. The next innovation is it's quite and again, they didn't come up with this innovation, but they're the first one, I believe, to apply it at a well-known model. All large language models during pre-training predict the next token. And the typical way to do that is that you use the negative log likelihood of the next token, and that's called perplexity. That's what we call that loss. And each model is then trying to predict the next token, just one token ahead. So there was some work done in a paper a year ago which showed that if you predict more than one token ahead, you can get some improvements in both latency and even performance. So what DeepSeek v3 does is it actually uses the next two tokens. It predicts the next two tokens, not one. So n, you could have n. Here you can see we've got 4 inputs and 4 outputs. This is a diagram from the paper. But it's predicting 2 tokens ahead at a time. So we can see here on the performance numbers over here, by going to multi-token prediction, most of the benchmarks improve, with the exception of MMLU. And even the original theory for multi-token prediction was that for multi-choice questions, and this won't work as well. And we can see that playing out in the results here. Slight drop in performance there. But for other benchmarks, we see an improvement. The next optimization that we see in DeepSeek R1v3 is how they use devices. So a lot of people have written about the fact that the company were GPU poor compared to maybe some of the larger companies pre-training large language models, and they had to squeeze the most out of their resources. So this is a technique for making more use of the GPUs available called dual pipe. So traditionally in deep learning, when you're training a model, you have what's called the forward pass. This is where the input training samples go through the network. And you can see here, these white dots are where GPUs are not being used. So if you're doing model parallel training, which you have to do for large language models with an algorithm like deep speed 0, then for the first, you can see for the first set of forward passes, these devices are not used, and only all of them are used when in this case the layers in the network are copied across, because that's kind of the way deep speed 0 works. So we can see there's quite a lot of white spaces not being used, and the traditional forward pass, backward pass, and then optimizer steps, you can basically play around with those and interleave them more, and you can parallelize them using this dual pipe technique. And this is the first paper I've seen in a large language model that applies this at scale, and it works quite well. So there's a lot of work they had to do in CUDA optimizers and lower level details to make this work correctly. Another optimization which seems pretty straightforward is to go to FP8 training. So you'll probably be familiar with tensor cores, which use mixed precision FP16 training. Well, we go down from 16-bit floating point numbers to 8-bit, and it reduces the amount of memory that's needed. So it improves throughput and reduces the amount of memory required. And they got this working. Microsoft released a paper on this over a year ago, but now it's running in production. So at the higher level, what's really, really interesting about DeepSeek R1, and it is innovative, is it's completely open source. So all the weights, all the techniques they've used, they've made open source. When we use DeepSeek v3 and write in a prompt, we'll get the complete chain of thought returned. OpenAI are not doing that. If you're curious, they'll return a summary of the chain of thought. So you'll get an idea of the model is thinking, but you won't be able to take that summary and use it maybe as training data for your own chain of thought model. But you can use DeepSeek R1v3 as a kind of trainer model if you want to use its output to train your own model. Now we're going to look at running DeepSeek R1. The problem is it's a really big model. It's 671 billion parameters, and that's over 1,300 gigabytes of GPU VRAM. And if you look at a state-of-the-art A100 GPU with 80 gigabytes, that's more than you'll get even on a GPU server with 8 GPUs at A100s. So you need a lot of memory, GPU memory. 16 GPU server with A100s will probably do it for you. If you split it up over multiple servers, you'll need a very high throughput network, so hundreds of gigabits. But what you can do is you can run the quantized version. So Unsoft have released a bunch of quantized versions, and these versions will run on a smaller number of GPUs. So today we're going to look at just running on two A100s, so we can fit in the fair and good. This is Unsloth who consider them fair and good, better and best. That's their qualification for them. But you can see that what's happened is that when they quantized the model, and the mixture of experts bits were reduced all the way down to 1.58 bits, which is very small. But they didn't do a homogeneous quantization of all the weights in the model. They're actually a lot smarter than that. So for example, where we have the gating coming in, so when the input comes in and the model has to decide which experts it's going to route that to, it's going to route that input request to, and they didn't quantize those weights because it's very important that the input is forwarded to the correct experts. But then the experts themselves, their weights were quantized heavily, we can see here. And the performance is still very good. So quantized models, DeepSeek R1, great. The other one that was released were the distilled models. Distilled models are very different. They're not really comparable, because what they did was they took existing models like Qwen and Llama 3.1 and they fine-tuned them. So what they did was they stored 800,000 data samples in DeepSeek R1 and then used those in supervised fine-tuning to fine-tune these models to become chain-of-thought models. They're not originally Llama 3.1 and Qwen are not chain-of-thought models, but they basically did this. And the way you do it is you have your large teacher model, in this case, DeepSeek R1 v3, and it's transferring its knowledge and capabilities to the smaller model, the student model, and it's doing it with those 800,000 data samples and supervised fine-tuning. This doesn't work great, let's be honest. So we'll show you how you can deploy this in Hopsworks and Kserve, but it's not where we're going to be, I think, in the near future. We're going to work more with quantized models and then fine-tuned versions of the quantized models. Okay, so that was DeepSeek R1 v3. How does that relate to sovereign AI? Well, the reason why I think the markets were also confused about DeepSeek was that a lot of the big tech, AI plans for 2025 have been derailed by DeepSeek. So the idea that everything has to run in their data centers on their software is problematic. And, it means that places like, let's say, the European Union, who are being more known for regulation than innovation, they can actually get into the game now. They're not going to be behind technologically. And that's because the model is open source. Everything is open source. And, if you think that, well, hang on, this is a Chinese model trained by a company in China, and when I send a request to DeepSeek.com, it stores my data, so the Chinese are getting my data. Sure, that's because that model is hosted in China. But you're able to take that model, download it, install Hopsworks in your data center anywhere in the world, and then host it from within that data center on Hopsworks. And then you now have the benefit of data protection, regulatory compliance, data sovereignty. You can fine-tune to reduce risk for model bias. You get performance and costs then as well, because you'll be able to control costs by having your own accelerators that you can use. So maybe we're using NVIDIA this year. Maybe we'll use AMD next year to reduce costs. And then, of course, if you maintain your own data for fine-tuning or using RAG with these next generation large language models, that can be your sustainable competitive advantage in your particular domain. So the general benefit of sovereign data and sovereign AI for large enterprises, organizations, countries, or even economic zones is that at the moment, there's an assumption that these AI service providers, what we can call intelligence on tap or intelligence service providers, they deploy their models at very large cloud providers. And these are often codependent, because we know there's a lot of talk about how to optimize energy use and keep data centers optimized for GPUs and so on. But a lot of, your money goes to those, and then you get your answers back and so on. And that's great. But the ability to be able to run this yourself can open up a lot of possibilities for companies, organizations, countries, and even economic zones. and Hopsworks will enable that for you. And the reason why is Hopsworks is a complete platform for the development and operation of AI applications at scale. So it manages compute, it manages GPUs, CPUs, memory, storage. It has the industry's most sophisticated platform for managing that data for training and inference. And there's support for storing models at scale in the model registry, which is optimized for K-Serve. K-Serve is the open source model sharing infrastructure supported by Hopsworks, which also has support for VLLM, which we'll see later on. There's support, of course, for monitoring and observability of these larger language models, which you need. And of course, this is an enterprise platform, so all of the enterprise security, compliance, auditing capabilities that you need are there. And it builds on top of lakehouse data. So large volumes of low-cost storage of data are built into Hopsworks, and then real-time data comes through its own database, an open-source database called RonDB. So if you use Hopsworks then to manage these large language models at scale, what do you get? Well, the first thing you want to do is manage your resources. So typically that means GPUs. And Hopsworks is organized into projects. You can have many different projects, and you can give quotas for projects. Say this project gets this quota of GPUs. You can say this particular server, here we have some servers. I've got a server here with 2 GPUs, H100s. I can dedicate that to a specific project. So just one team could work on that using node labeling. This is all running on Kubernetes, by the way. And then there's priority scheduling. So if you're running longer term fine-tuning jobs, and then you have interactive jobs or serving jobs, they'll all have different priorities for different organizations. And the things that you want to do, apart from managing GPUs, is you want to fine-tune models. And so that is supported with Ray, and Hopsworks is typically a popular framework for doing that. Serving the models, again, K-Serve on VLLM. And you can take any open source model, not just DeepSeek, Llama 3, Mistral, they all run on Hopsworks today. And then RAG is supported, of course, on Hopsworks, not just through using libraries like LangChain, but there's support for vector index built into Hopsworks, and even support for getting at your lakehouse data through function calling. Now, sovereign, when you're deploying your infrastructure, you can think it can be sovereign within a cloud environment. So within any cloud environment, Hopsworks can be deployed inside your cloud account, and no data will leave your cloud account. So there's a managed control plane you can use if you want to for deploying, upgrading, scaling up and down, creating backups and restoring, and so on. Or what you can do is you can deploy Hopsworks in an air-gapped environment. And this is often in what we call an on-premise data center. So disconnected completely from the internet. And Hopsworks will work and run fine in all of these environments. So I'm going to talk a little bit about fine-tuning and serving before I hand over to Abby for a demo. So fine-tuning for, in particular, if we talk about fine-tuning DeepSeek R1, it's very early. In general, you want to fine-tune to have a model work better on a specific task. So maybe you've got to get a specific format for the replies you expect from your chatbot, or maybe you want to enhance it with certain capabilities. You can do that, and it's a lot cheaper than pre-training a model, which requires huge amounts of data. So you do need some label data for fine-tuning. And the label data is different in DeepSeek or R1v3. It's not like our traditional Llama 3.1 Quen models, because the data that was used to train it is a little bit different. We have, of course, the pre-training data that we start with, which is not shown here. But post-pre-training, what we see in DeepSeek RV1 is there's some supervised fine-tuning to bootstrap the oral agent, improves readability of the answers. Then we have this very long, where we talked about the reward model with the reasoning tasks. So this is all reinforcement learning. And then there's another supervised fine-tuning phase with sampling, so rejection sampling. So saying, well, this is not a good answer, this is not a good answer, and this helps for more general purpose capabilities. And finally, then there's preference-based tuning based on oral AIF, which is rule-based reinforcement learning. So you can have different data sets which can add different capabilities. It's very early to say exactly how people will fine-tune and what the trained data sets people use for fine-tuning will be. Will it be supervised fine tune it with instruction data sets, or will people be adding additional reasoning capabilities? It's too early to kind of speculate on that, but what we see people doing today are fine-tuning the distilled versions of DeepSeek R1. So this means the Quen or the Llama versions. And this is typically done with LoRa or QLoRa. You have an instruction data set, and then we're training these LoRa adapters and keeping the actual model then and its weight static. But like this is just a temporary phase, I believe, because the distilled models, we don't see enough evidence that they're going to be good enough. When you're training or fine tuning these models, you really need to understand GPUs, and you want to maximize the utilization. So when you're training, you want to make sure that this utilization is as high as possible. And there's a lot of layers where utilization can drop. It could be the interconnect between the GPUs, which if you're running on a good GPU server, that will be up to 200 gigabytes per second. But it could be then if you're trying it out on your own and the model doesn't quite fit into GPU memory, and you offload some of the layers into the host memory, well, now a lot of traffic will go through your PCI bus. And if it's only a PCI 3 bus and 8 gigabytes per second, it will not work very well. So you typically, this is another place where you can have bottlenecks, your PCI bus. Obviously, if you're fine-tuning a model from local disks, you're going to get very high throughput. But if you're not, if you're trying to fine-tune a model from S3, and we'll see in the models that we download, even the quantized models, the files are big. They're 30, 40 gigabytes, and S3 will only typically give you about 200 megabytes per object. So you may have 32 gigabytes free in your PCI bus, but if you're only reading 5 files in parallel of 200 megabytes per object, you're only getting a gigabyte through here, but your network might be a lot higher. So how do you kind of, avoid these bottlenecks? That's something that we work on heavily in Hopsworks. Just to give you an idea of one of our contributions here, when you read from your S3, there's an internal file system, a tiered file system in Hopsworks called HopsFS, which can store the latest copies of data, latest versions of the files in local NVMe disks. And this can massively improve rereading the data for training. So instead of going to S3, it can go to local NVMe disks transparently. You don't need to change anything in your code. And you get massive improvements in throughput. And that can be done both for training, fine-tuning, but also even in inference, loading your models as well, which can be quite slow when they're hundreds of gigabytes in size. So I'm going to just finish up by just mentioning briefly how we serve models in Hopsworks. We support Kserve and VLM, and we, of course, add support for access control, authentication, logging, metrics, and of course, integration for RAG and other things like creating features or guardrails that you typically would have in large language models. And these services can all integrate with the data platform that Hopsworks has, providing a feature store and vector index, model registry, and more. So with that, I'm going to hand over to my colleague, Javier, who's going to show you briefly Hopsworks and DeepSeek R1. So let me just kill my Javier, over to you.
Yeah, hello everyone. Let me share the screen here. Right. So what I'm gonna show today is how to deploy the quantized version of DeepSeek R1 using Llama CPP, and also how you can deploy the distilled versions of the DeepSeek model with Hopsworks. So the reason why is because at the moment VLLM, which is the tool that we use to deploy these LLMs, does not fully support DeepQ R1 at the moment, but it supports already the distilled version. So you can see the Hopsworks interface here. I created a project which is called DeepSeek. So projects can be seen like isolated spaces for managing your machine learning assets, although you can share these assets across different projects. And also projects help you manage the compute resources that are in the cluster, as Jim was mentioning before. So, for example, in this cluster that I'm running, I have 5 nodes, and one of them is the H100, which basically has 2 GPUs in it, and they are currently used by this Jupyter server instance here. So the way that the project helps you managing the resources is basically that you can create quotas for allocating these resources to specific projects, or you can specify where you want to run a model deployment, where you want to run a Jupyter server, and other different compute components that are supported in Hopsworks. So as you can see at the moment, I have a Jupyter running here. I specified that I want the 2 GPUs, H100, that are available in one of the nodes. Also 16 cores and 204 GUIs. So as well, you can see that you can pick different Python environments. So within every project, you can basically create customized Python environments. So in this case, as I mentioned before, I'm running DeepSeek R1 using Llama CPP. So what I did to make it easier for me was basically clone one of the pre-built Python environments, and I basically run the following custom commands, which are provided by the in this blog post by the Anslot team. That is basically the team that is providing the quantized model files for the DeepSeek model. And yeah, basically I can specify which commands I want to run. In this case, I was building Llama CPP with different configuration, and created this Python environment here. And then basically I started the Jupyter instance specifying that environment here. After doing that, I can go here to the Jupyter instance, and we can see if we run NVIDIA SMI on the container, I can see that both GPUs are available here with 80 gigabytes each. So all 61 layers of the model can fit into the GPUs. And basically to run it, what I did was to use the Hugging Face Hub library to download GDUF models that are provided by the Anslot team. These are the quantized files. And then I can proceed with the Llama CPP tool that I was compiling before. So it's already in the environment because I picked the customized environment to run this instance. And we can see here that it started loading the model into the GPUs. Keeps going here. And then, yeah, basically I use the same prompt that is in the blog post. It's basically, I was asking if the model can create a Flappy Bird game in Python. So at the beginning, we can see that, actually, if we look for it, it might be easier to see. Yeah, it receives the prompt, and then it starts thinking and trying to resonate with itself how to build this game, and start running the different components that are needed, and how to build a Python program, and so on. And then at the end, after the think predefined token, we can see the final answer that will finally be sent to the user. So it's basically that you can create the game here, and with all the code, the Python code for the game. And at the end of the execution, Llama CPP provides the throughput of the tokens. So in this case, we can see that for the different steps of the inference process, it reads, for example, for the context here, evaluation time, yeah, a bit more than 7 tokens per second, and so on. So we can see some metrics here as well. And then if you want to deploy the distilled version of this model with Hopsworks, I have another notebook here. It's basically, I use the same library from Hugging Face to download the model files. And in this case, I decided to download the distilled version based on the QM model. And to deploy the model with Hopsworks, basically what you want to do is first register the model into the model registry. So for that, Hopsworks provides a Python API that helps you interact with the platform. And basically, you can do most of the things via Python that are supported on the platform. So basically, in this case, I start first getting a handle of the project by using the login method. I get my model registry handle, and then I define the metadata of the object for a model. So in this case, I just provide a name and a description, and call save on the local directory where I downloaded previously all the model files. And then after that, you have two ways to deploy the model Hopsworks. So we use under the hood, we use Kserve to operate the deployment of these models. And then inside the model deployment, we run the VLLM engine to actually load and make inference with the model. And there are two ways that this is supported in Hopsworks. You can provide a customized predictor script, which basically helps you be more flexible in the way you want to deploy the model. If you want to do some additional steps, for example, while applying the chat template or something like that, or you can just default to use the already provided image from the VLLM team, which already implements an OpenAI compatible server. So in this case, to do that, you basically don't need to specify the predictor script. You just need to pass a configuration file. In this case, this is the configuration file that I'm passing here. And these are basically the arguments that will go to the VLLM engine. And for this model, we basically need to enable reasoning and specify that the parser for the reasoning is DeepSeek. And this will help the VLLM engine to know basically what is the chat template of how you can interact with the model in the end. And after that, you create the deployment and you can start it and so on using the Hopsworks API. And it actually, you go to the UI, we have here the model registry on our left-hand side, and we click on the model that we just registered. There is only one version in this case. And we can see here the description that we chose here, and also as part of the model files, there was a README file that is already also in the repository of Hugging Face, and we can see the README file from DeepSeek and so on. And you can, if you deploy different versions, because maybe you want to fine tune some other models or do some other experiments, you can also export different metrics per version. And as well, you can go to HopsFS, as Jim explained before, and see all the files that are registered for this specific version. So we see models here, name of the model that I was registering, the first version, and all the files. We can see them here with the tokenizer config.json and the safe tensors. And then also on the left, you can click on deployments, and you see the deployment that was created, that is in this case using the VLLM OpenAI provided image with the implementation of the OpenAI server. And you can see information of the model artifact, like the configuration file that you are using to basically configure the VLLM engine, which model and which version are you want to deploy, the different endpoints that you can use to reach the model and make inference here, and also the configuration for the resources that you want to allocate. In this case, we need a GPU. With just one GPU is enough in this case, and that's and then basically we will make sure that these resources are allocated for the model. to be deployed. And I think that's pretty much what I wanted to show today.
All right. Thanks, everyone. I don't see any more questions there. So with that, have a great rest of your day.